Continuing 10.6, we're on to the damping part. When the conductor moves into or out of a magnetic field, an eddy current is created in the conductor. Now that means it's a current that's there within the metal, but it never comes out of the metal. As the conductor moves into the B field, the flux increases. This produces a current by Faraday's law and is directed in a way that opposes the change in flux. This current's magnetic field causes a force on the conductor. The direction of the force will always be opposite the motion of the conductor. For example, here is a flat metal pendulum entering and leaving a magnetic field. If we start over here on the left, draw a circle to represent the current that's formed, because this flat piece of metal is going from no magnetic field to some magnetic field. So the flux of that flat piece of metal is increasing. Since it's increasing, there'll be a current that creates a magnetic field the opposite direction, because we want to cancel out the increase in flux. So grab the circle with your fingers in the middle of the circle. So this is one with your fingers curled. They'll curl up to the center of the circle, and your thumb will naturally point counterclockwise around the circle. So your fingers are coming up here in the middle. Your thumb will be pointing that direction. Then we're going to take and use the right-hand rule on this current, because if we have a current in a magnetic field, it experiences a force. So the magnetic field is down into the screen, so this time with your hand flat, point your fingers down into the screen. Your thumb goes the direction of the current, so if we do this point right there, that point, then your thumb should point that way, because that's the direction of the current at that point. So fingers into the screen, thumb pointing the direction of the current. Your palm should then face the direction of the force. And you can see the direction of the force is that way, opposite the motion of the pendulum. We do the same thing on the other side. Okay, as the pendulum leaves the magnetic field, the flux is decreasing. Since the flux is decreasing, we will induce a current that makes a magnetic field that goes the same direction as the ones there to try to keep the flux from changing. So since the flux is going down, we want to increase our magnetic field. So your fingers will go down in the center of this loop, and that'll cause your thumb to point this way clockwise. Then using the flat hand right-hand rule, your fingers right here, your fingers are going to go down into the paper, into the screen. At this point, the current is going that way. So your fingers are going into the screen. Your thumb is pointing up the direction the current is going at that moment. And your palm then will face this way. That's opposite the direction of the movement of this pendulum. The pendulum is actually going out of the pendulum's actually going up out of the magnetic field, but the force is backwards down into the magnetic field. This is actually used. My big balance at school uses this exact same principle to keep it from bouncing all over the place and trying to find the mass of something. It has these magnets and a big metal fin like the pendulum, and it keeps it from moving around. It's also used on roller coasters as a safety brake, a nice simple brake. Has metal fins in the track and magnets on the cart, and as they go over the fins, the metal fins, there's a force just slowing down the roller coaster cart. It's also used, oh, there we go. stopping the balance from moving. Brakes on trains and roller coasters. Now, it's based on the speed that it's moving, so it'll never bring it to a complete stop, but it does slow it down nice and smoothly. With no sliding parts, it's not affected by rain, oil, anything like that. It will always slow you down. You can also use motional EMF and damping to sort recyclables. So in this example, they have the truck just dumping stuff down this ramp with a magnet under it, and even non-magnetic metals will have this magnetic damping and will have a force opposite the motion. So the metals will go slower down the ramp, and the things like paper will go down, slide down faster because they have no motional EMF, no damping to slow them down. So the metal objects will move slower down, they get sorted. Another example is a metal detector. The primary coil has an AC current. This induces a current in the metal. Because the current, remember, AC is alternating, so it goes one way, then the other way, and then back the first way. The induced current creates a magnetic field, and the secondary coil gets an induced magnetic field, creates a current in the secondary coil, which sends a signal to the user. So the primary coil has an alternating current. It sends that out, and it induces a current in the metal through the motional EMF, because the current keeps changing. And then that induced current in the metal creates a magnetic field that's changing, and this changing magnetic field then induces a current in the secondary coil of the metal detector, and you get a signal. And that's it for today. Have a good day.